Bismillahirrahmanirrahim. So let's look at one more property, which I personally like. It's actually modulation property. Modulation property. I personally like this property. I don't know, because it relates to communication system, and it talks about how actually modulation takes place and how do you shift signal from time domain to frequency domain. All right. So in order for me to do that, let's do the same thing. Let's try to prove that property. So let x of t as a Fourier transform of x of f. All right. Then x of t times it by cos 2 pi f naught t should give me f 1/2 x f minus f naught plus 1/2 x f plus f naught. All right. So we're trying to prove a modulation property. Modulation property is this, that x of t is being multiplied by some signal cos 2 pi f naught t. Right? And we're trying to prove this property. Right? So according to Fourier transform, if I were to just look at the table, I would come to know that x of t multiplied with cos 2 pi f naught t, when I take a Fourier transform of it, it would be 1/2 x f minus f naught plus 1/2 x f plus f naught. All right, guys. So if you look at it closely, this is similar to what we have calculated for cos function. If you look at it, when we were calculating a Fourier transform of a cos function, it was actually delta 1/2 delta f minus f naught plus 1/2 delta f plus f naught. So let's go through it and let's try to calculate the Fourier transform of it. So let's prove. So let's do a small proof by working out the example actually. So Fourier transform x of t cos 2 pi f naught t. This is going to be, as t goes from negative infinity to positive infinity, all right, x of t cos 2 pi f naught t, whole thing multiplied by e to the negative j 2 pi f t dt. All right. So if you recall this is just the definition of Fourier transform. We're using this whole thing is just x of t, and this is that kernel of Fourier transform. All right, guys, if you recall this, now it is quite easy. Let's just forget about this for a moment, and let's have t as it goes from negative infinity to positive infinity. And I'm going to apply my favorite Euler's identity here. So this is just going to be x of t, and here I can apply my identity, which is e to the negative j, I think e to the positive j 2 pi f naught t plus e to the negative j 2 pi f naught t, whole thing 2, and then I have this kernel e to the negative j 2 pi f of t dt. This whole thing is being multiplied together like this. So I can just split it. I'm going to keep this as is, just like we did it in when we were calculating the Fourier transform of a cos function. So this is just like saying t as it goes from negative infinity to positive infinity. All right, I'm going to bring that 1/2 out. So this is going to be a 1/2 out. That is going to be x of t e to the negative j 2 pi f minus f naught t dt plus 1/2 t as it goes from negative infinity to positive infinity x of t e to the negative j 2 pi f plus f naught t dt. Okay, what have I done here? So I've taken 1/2 out, which is common in both of these terms. X of t is also common, which is also common. So when I multiply this by this, all right, I get e to the negative j 2 pi, and I need to have it in terms of, so what do I do when I have power bases are same? I have to add them up, but there was a negative outside. That's why I have to bring this out, because if I were to distribute this negative now, this negative would make this positive. Right? Same thing here. Just like we did it when we were calculating the Fourier transform of the cos function. Now, if you were to look at it, what does this definition look like? This is, imagine this is being changed from t to f, and we're looking at it in terms of frequency domain. X of t is just going to be, what is the Fourier transform of x of t? It's just going to be some x of f value. And what is that f value? F is just going to be f minus f naught, 1/2 plus 1/2 x f plus f naught. All right. How did I get this? Let's just look at it closely. If I were to change this t to f, what does it look like? It actually looks like a Fourier transform or something. Okay, Fourier transform what? If this is x of t, what is the Fourier transform of this? This is just x of f. All right, it's not just x of f. Now this kernel is being shifted in either a negative side of the frequency or positive side of the frequency. So it's f minus f naught, 1/2 x times f plus f naught. So this is a very important Fourier transform that everyone should know. Is 1/2 x f minus f naught, 1/2 x plus f minus f plus f naught. So basically, let's look at it. What is it that, what does it mean pictorially? What is it? What is what it means? All right. Normally, when I make when we normally make a modulator is something like this. So here we have my x of t. All right, this is my information signal. Here's my cos 2 pi ft, and here's my output. So this should be x of t times cos 2 pi f naught t. All right, so what does it look like? We're multiplying it together. So two of these signals are being multiplied together. So x of t is somewhere in time domain, something like this. Let's say that this has some w, which is a bandwidth of this signal in time domain. All right. So now when I modulate this signal using cos, now what happened is this. Remember, okay, so we will compare this with just only a cos function. X, all right. This is x of t. All right. Let's just look at it. Let's say that this is x of t in time domain. The Fourier transform of this is just going to be some signal. All right, let's say that this is also some signal. This is the Fourier transform of this x of f. All right, let's look at a cos signal now. Cos is 2 pi f naught t in time and in frequency domain. Cos is this. Cos is something like this in time domain. Cos becomes this, isn't it? Minus plus f naught minus f naught. This is what cos becomes. Now when I take this signal and when I put this on top of this, so now we're saying this. We're taking a signal. It was actually what, when I just simply take a Fourier transform of a cos function, it's actually a delta function. 1/2 delta f minus f naught, 1/2 delta x, 1/2 delta f plus f naught. But when I take this signal will be shifted and will be moved on top of this. So this would become something like this. This will no longer bury the shape of bury a shape of a delta function. It would be some signal which is the representation of x of t. All right, so it's not going to be a delta function. It's going to be some signal that might have a shape, that might have some bandwidth associated with it. All right, so that's why you have this x in front of it. All right, that's why you have what, x to represent that it's not just some tone, it's actually a function, and my signal is being shifted this much in positive frequency and in negative frequency. So that's why in your textbook you might encounter signal, when I modulate signal, you might encounter something like this, where it says the reason the shape is just to show the bandwidth of a signal. So I hope you like this small tutorial on modulation property. of Fourier transform. But if you do have any questions, please do let me know, and don't forget to subscribe to my channel.